So the crossing at B, positive or negative?
Positive.
It's a positive crossing too. Because as I drive down this arc underneath this bridge, if I look to my left, I see the traffic on the bridge is going from my left to my right. So B is still a positive crossing. So that means we can still use this same magic average equation to relate the arcs together. Which arc is my bridge, my overcrossing? X2. So it gets the coefficient 1 minus t for my bridge. Which is my inbound arc? X1. And so it gets the t. Outbound is x3 now, so it gets the negative 1. And then a 0 over here. So those two were positive crossings. What about C?
So are we still following the car?
We're still following the car.
So would we hit D first?
Oh, you're right. We would hit D first.
Okay.
Yep. Let's do D.
So we do D.
Except that I'm driving over the bridge if I'm still following the car
Right.
at this point, right? And so in order to analyze D, we need to think about what the cars going under the bridge are going to see. Right? So at D, as I'm going underneath this bridge,
At D, and it's going. You're going underneath, which is looking to the left.
look to the left and I see the traffic going away from me. Look to the right and I see the traffic coming towards me. Because I'm now driving
Here.
this way.
Okay.
So is that a positive crossing or a negative?
Positive.
So we decided that D is an inverse crossing.
Right.
Because as we drive down this arc and we come to the crossing, come to the bridge at D, we're going to see the traffic there going from our right to our left over the bridge. So that's a negative, an inverse crossing. And then how about the crossing at C? It's also a negative, an inverse crossing, because as we're coming here to the bridge, we look to our right, and the traffic is coming over the bridge from right to left. So C is also an inverse crossing. So we have to, before we can finish building this system of equations, we have to figure out how the algebra is going to do an inverse crossing for us, right? Because it's not going to be the same equation as our magic equation, because we explicitly said that the magic equation was going to be the one that defined our positive crossings, not our negative crossings. So we just have to figure out how these two are related one to another. And the key observation there is that what really relates these two diagrams one to another is kind of an interchange of the roles of Z and X, right? That one way to look at this is that I'm reversing the flow of traffic on the bridge. The other way would be that I'm reversing the way that I'm driving along the arc that goes underneath the bridge. Right? And so my inbound arc used to be X. If we look at it as Z instead, and we look at the outbound arc as X instead, then we should get a way of determining the inverse operation. So let me do that on a blank page for a second, because we're going to need a little bit of room to breathe. So a positive crossing is defined by the equation Z equals Tx plus 1 minus Ty. Right? But if we interchange the roles of Z and X, then what we functionally have done is we've changed the orientation of that crossing from a positive crossing to a negative crossing by interchanging the roles of the inbound and the outbound arcs. So all we need to do now is just solve this equation for Z. This should seem like kind of a familiar process from your high school algebra classrooms. What are we really doing here? If you interchange two variables and then solve for... you're finding the inverse function. Yeah, that's what we're doing. So if I solve this for Z, I need to get that Z by itself on one side of this equation. So I'll subtract TZ from both sides. I'll also subtract X from both sides. Right. So that I'll have minus TZ equals minus X plus 1 minus Ty. And then I need to get Z by itself. So what should I multiply by here? Negative 1, we'll get rid of that negative sign.
And then 1 over t.
1 over t. So multiply by 1 over t, which I'm going to write as t to the minus 1. So I'm going to multiply both sides by minus t to the minus 1. That will get my z by itself. The coefficient of x is going to become minus a minus t to the minus 1, x. And then if I multiply 1 minus t by t to the minus 1, minus t to the minus 1, I'm going to get minus t to the minus 1 plus t times t to the minus 1. And what's t times t to the minus 1 better known as? 1. So I get 1 minus t to the minus 1, or 1 minus t inverse. And that then gives us the version of the magic average for an inverse crossing. It's the same as the magic average for a positive crossing, just replacing t with the reciprocal of t. Replace t with t inverse. So at least that's nice. We don't have to remember something completely new. We just have to replace t by its reciprocal. And we know that that reciprocal exists because we've explicitly included it in our algebra system. Right? So this is what x inverse triangle y is going to be defined to be. Okay. So coming back into our matrix that we're building, for each of our inverse crossings, we'll just use that equation instead. Let me recopy it over. X inverse triangle y is going to be t inverse x plus 1 minus t inverse y.
We can still move the z over.
And we can still move the z over. Yep, just like before. And so the outbound arc is still getting negative 1 for its coefficient, but the bridge is getting 1 minus t inverse, and the inbound arc is getting t inverse for its coefficient. So at crossing C, our bridge is arc 4, and so it's getting 1 minus t inverse as its coefficient. The inbound arc is x3, so it gets t inverse. And the outbound arc is x2, and it gets negative 1. And x1 is not participating, so it'll get a 0. And we'll do the same thing with D. The bridge is x3, and so it gets 1 minus t inverse. The inbound undercrossing is arc x4, so it gets t inverse. And then the outbound arc is x1, so it gets negative 1. x2 doesn't participate. So this then is a 4x4 matrix that encodes the adjacencies of the oriented arcs of the oriented figure 8, the way that it's sketched here. If we had used the opposite, so the amphichiral opposite of this that we actually started with a few minutes ago, what would change, do you think?
I feel like A and B would be inverses and C and D would be.
Exactly. Yep. All of our positive crossings would become negative and vice versa. And so in principle, you would think that affects a change in the properties of this matrix. And in principle, it does. But for the figure 8, which we've convinced ourselves is amphichiral, it should make no difference. So that's an interesting observation. Let's put that over in a parking lot somewhere. I don't have much room on this slide, but observation. Taking the amphichiral opposite, or chiral opposite, I suppose is a better way to say it. Chiral opposite, switching my overs versus my unders. Really what it does is it changes the inverse crossings into positive crossings and vice versa, which has the effect of changing t with t inverse everywhere that we see it in this matrix. Right? That's all that would happen if we took the opposite. So that's kind of cool. That also means that if I have an amphichiral knot like this one, then any knot invariant that we distill from this information needs to be left invariant by changing t with t inverse. Right? If I switch out t for its reciprocal for an amphichiral knot, then all of its not invariants need to remain the same because the not remains the same. Right? So let's hang on to that too. Thus, amphichiral means symmetric with respect to switching T with T inverse. So when we discover, for example, a polynomial associated with this knot or something like that polynomial, if it comes out of this data, should be insensitive to switching T with T inverse. Okay, so that was, I think, the hardest conceptual part, and we weren't quite ready for that in our last class, so I'm glad that this question necessitated having this conversation. So now we know that this matrix is going to encode the colorability information, all the colorability information for the oriented figure 8 knot. And then we can go through the process of trying to compute determinants. Now we know, based on what we talked about last time, that if I take the determinant of this 4x4 matrix, that I'm certainly going to get 0. Let's ask Sage to do that in a minute here, just to verify. And then the second thing that we wanted to find, so last time we talked about the Alexander polynomial as a kind of a two-step process. The first, we'll take the determinant of this matrix, let's call this matrix M. The determinant of M is going to be 0, always, necessarily. The reason for that is we know that the kernel of this matrix is always non-trivial, because the kernel contains all valid colorations of this knot, and the trivial colorations are always valid. So that means that the kernel of this matrix is non-trivial. Therefore, there's always at least one free variable, which implies that the matrix is not invertible, which means its determinant must be 0. But the other piece that we wanted is we wanted the first subdeterminant. In other words, after we do just enough row operations on this matrix to clear out the bottom row, basically. Once we do enough row operation to clear out the bottom row, there is an upper left 3x3 matrix that we can find a determinant of, and that determinant is supposed to give us the Alexander polynomial for this knot. So then, let me indicate that on this screen somehow. So if I highlight this 3x3 subdeterminant, that this is going to equal delta of k, our Alexander polynomial. Now you'll notice I've just, what looks like I've committed a faux pas here. It looks like I've just done this without row reducing. Last time we row reduced, and then after we did some row reduction, we took that 3x3 determinant. But in fact, it doesn't matter. In fact, just taking the determinant of that 3x3 block will give us the same answer if we agree to normalize our Alexander polynomials in the same way. That's supposed to be really good news. It means we don't have to do row reduction at all as part of the process of finding the Alexander polynomial. We just have to find a 3x3 determinant, which admittedly is still kind of nasty, but it's at least better than having to row reduce and then find a 3x3 determinant. So maybe let's leave that example here for now. I just want to take a quick moment and just review 3x3 determinants real quick, because we didn't actually last time take a full 3x3 determinant. So just to refresh our memories, let's say that I have a 3x3 matrix. Let's put in some fake entries. 1, -2, 3, 3, 1, 1, 0, 2, 4. So here's a 3x3 matrix, and I want to find the determinant of M. So there's there's probably a bunch of options, but there's two main options that we take for computing determinants. One strategy is to row reduce. This was a strategy we were using last time. And if I row reduce using only row addition, in other words, adding a multiple of one row to another, that operation leaves the determinant unchanged. And so if I'm able to row reduce using only row addition, Then all I have to do is multiply the diagonal entries once we have zeros below the diagonal. So let me just quickly do that with this example, just to illustrate the concept. So if I want to clear out this 3, I'll take row 2 minus 3 times row 1. It's going to be 0. 1 minus 3 times negative 2 is 1 plus 6. That's 7. 1 minus 3 times 3. 1 minus 2, 3. And then also, well, my bottom row is still fine, 0, 2, 4. And then if I want to clear out that 2 that's still below the diagonal, what I can do is take, all right, here comes some fractions, unfortunately. Row 3 minus 2/7, row 2. And that should be enough to cancel out a 2 using a 7. Top rows remain the same. My middle row, 0, 7, negative 8. And my bottom row, 0, 0. And then we're going to have a nasty number probably. 4 minus 2/7 of negative 8. That's 4 plus 32 over 7. I hope. No, 4 plus 18 over 7. 16. 4, yeah, sorry. 4... But it's plus, right? Because negative 8 times. So 4 plus 16 over 7. 44 over 7. Okay. Thank you. End of the day, and my fraction arithmetic is not up to par. So now we've done all the row reduction to get zeros below the diagonal, and we've only used row addition operations to do so. Those leave the determinant unchanged, so the determinant of this is equal to the determinant of this, and the determinant of any upper triangular matrix, so only zeros below the diagonal, is the product of the entries on the diagonal. And notice also something else convenient that happens is that this denominator gets cleared when I multiply it by the 7. That's a trick that I learned by observing a faculty colleague of mine teaching linear algebra early this week. Actually, last week I was sitting in and I was like, oh, you know what? I never thought about that. Yeah, so when I multiply those entries on the diagonal, we end up getting 44. 1 times 7 times 44/7 is 44. So that's one way of taking a determinant using row operations. The other way, because we want probably to avoid row operations in our not polynomial land, because they're kind of nasty, the other way to do it is called cofactor expansion. And what this does is it takes a 3x3 determinant and it writes it as a combination of 2x2 determinants. And since 2x2 determinants we know how to compute, diagonal product minus antidiagonal product, that allows us, after one cofactor expansion, to compute the determinant of this matrix. So how that works is you select a row or select a column, and I'm going to select the first column just because it has a 0 in it, so that's going to be kind of convenient. So I'm going to select a column, and first of all, assign signs, either plus signs or minus signs, to the entries in my matrix with the rule that the first entry in the upper left always gets a plus, and then every adjacent entry gets the opposite sign to the ones it's adjacent to. So that means that this one would get a minus, this one would get a plus, minus, plus, minus, plus, minus, plus. Right? So we put those little signs in there. We're going to use those in a minute. What we then get are called the cofactors in this column are going to be 1, positive, -3, and 0. So those are my 3 cofactors. I'm going to write those down here, 1, -3, and 0. And then each one of those cofactors gets multiplied by what's called its associated minor. And a minor is a 2x2 matrix that we get by crossing out the row and column that that cofactor lives in. Right? So associated with the cofactor 1, we're going to cross out the row and the column that that 1 resides in. So I'm going to scrub that, I'm going to scrub that, and I get this 2x2 matrix. And we're going to multiply that determinant by 1. Right. So what I'll do is, let me write that down here. So that matrix was 1, 1, 1, 2, 4. So I'm not going to use those signs. Those are just for the cofactor part of it. 1, 1, 2, 4. So I'm going to take the determinant of 1, 1, 2, 4. I'm going to multiply it by the cofactor 1. When I cross out the row and the column of this cofactor, I'm going to get the matrix negative 2, 3, 2, 4. And that's what multiplies my negative 3 cofactor. Negative 2, 3, 2, 4. And then finally, when I cross out the 0 row and column, I get negative 2, 3, 1, 1. And that ends up getting multiplied by 0. And hence the reason that I chose the first column for this cofactor expansion, because I don't care what this 2 by 2 determinant is, it's just going to get multiplied by 0 anyway. So it reduces it, it gives us a little bit lighter lift. The more that you study linear algebra, the more that you pick up on these little tricks, and there's a lot of linear algebra that has to do with what are called sparse matrices. These are matrices with a whole lot of zeros in them. And so for sparse matrices, cofactor expansion is really nice for computing determinants, because anytime there's a 0 in the row or the column that we expand across, that subdeterminant just gets wiped out anyway. So it gives us a little less to do. So let's just calculate this and verify that we have what we expected we'd have. So the determinant of 1, 1, 2, 4 is going to be 1 times 4 minus 1 times 2. And then I've got minus 3. And then this determinant is negative 2 times 4 minus 3 times 2. So that's going to be 1 times 2 minus 3 times negative 8 minus 6. That's negative 14. And that's 2 plus 42. 44. So there's some justice in the universe. We got the same answer using both of these approaches. But again, as far as our not journey is concerned,
So where do you use it for cofactor?
cofactor is probably the quicker route to get home.
Okay.
Besides, it turns out that our figure 8 matrix that we were working with, even the subdeterminant that we want to compute does actually have a 0 in a couple of its entries. So if you choose the cofactor expansion across one of those rows or columns, you'll save yourself an extra 2 by 2 determinant. The only remaining caveat is that the determinant that you get is not necessarily exactly the same thing as the Alexander polynomial, because of the convention that we want to multiply by enough powers of t, multiply it by enough t's, to make the constant coefficient positive. To make the constant coefficient positive and all exponents positive. Because we want the Alexander polynomial to be a polynomial and not a Lagrange polynomial. So we don't want there to be negative powers of t in our answer. So all we'll do is just multiply our answer by enough powers of t to make all the exponents positive and all of and the constant coefficient also positive. So as an example there, let's say that I did all this work, and let's say that the answer that I got out of it was something like negative 2t to the minus 3 plus 3t to the minus 1 minus 4t squared plus 2t to the third or something. Let's say that this was the answer that I got. This is not what we call the Alexander polynomial, although it happens to lie in the same span as the Alexander polynomial that we want. To normalize it, we just want to get all of the t's, get all the t exponents to be positives. So what should I multiply by here if I want to make all the exponents on my t's positive? T to the third will do it. Yeah, exactly. So then that's going to give me negative 2 plus 3t to the second minus 4t to the fifth plus 2t to the sixth. And then I also want to get my constant coefficient positive. It's the easiest way to do that. Yeah, just multiply by negative 1. Just flip the signs on everything. So then we would call this version the Alexander polynomial, now that we've gone through the normalization process. Because otherwise, if we don't agree on this normalization procedure, you and I can get different answers, if we choose different 3 by 3 minors of this matrix. So here I'm choosing the upper left-hand one, but what we ultimately want is we want the answer not to depend on which of the 3 by 3 minors we choose. If we want to get out of doing row reduction, then we need our answer to be independent of which 3 by 3 minor in this matrix that we choose. And that's only possible after we agree that we're going to normalize our answers in the way that we talk about here. Right? Otherwise, you and I can get different answers, but they will always differ by a constant multiple of t to the some power. Right? So once you and I normalize in this way, we're going to get the same answer for Alexander polynomials.